All right, so today we're going to be talking about instantaneous and average power first. And this is going to be a review of material that was covered in circuits 1. And then once we wrap this up, we're going to be talking about the maximum average power transfer function. And the person that taught circuits 2 last borrowed my notes and did not return my notes for that part. So I'm going to be teaching it straight out of a textbook, but it'll be okay. All right. So instantaneous power and average power. Let's say that we have a black box network. I know you guys are thrilled. And this network is sinusoidally excited. And we are able to measure the voltage drop across the network as well as the current flowing into the network using, say, an oscilloscope or something like that. Okay. So since it's sinusoidally excited, we know that our voltage V of t should be of the form Vm cosine omega t plus some phase angle theta v. And our current I of t should be of the form Im cosine omega t plus some phase angle theta I. The instantaneous power absorbed by our network will simply be the product of V of t and I of t. So that's going to look like Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. And using a trig identity, this looks like 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So if I were to plot this as a function of time for generically an inductive load, it would look something like this. So I'm going to put this dashed line right here. And this dashed line is corresponding to this portion, right? So 1/2 is a constant, very obviously. The magnitude of our voltage is a constant. The magnitude of our current is a constant. The phase angle of our voltage is a constant. And the phase angle of our current is a constant. So 1/2 times Vm times Im times cosine theta v minus theta I does not vary in time literally at all. So we're going to have some DC portion. And then on top of that, we're going to superimpose some AC portion. So this is just going to look like a sinusoidal wave, right? So something akin to this, okay? So the red part is the AC portion superimposed on top of the DC portion. And imagine, if you will, that these were the same size on either side of that dashed line, like I was capable of drawing this correctly. Okay. All right, so what does that dashed line bit represent? Yep. I'm going to ask my question again. What does the dashed line in this graph represent? DC part, right? But obviously that, because I told you that explicitly, but we have a sinusoidal signal, and exactly half of the time our sinusoidal signal is above that dash line, and exactly half of the time that sinusoidal signal is below that dash line. So the dashed line represents the average power that is absorbed by our load. So this is literally going to be our average power. Now, back in circuits 1, I also mathematically derived this relationship. I'm not going to waste our time doing that again. If you want to see the derivation, you know where my shitty YouTube channel is, and you can go look that stuff up. Okay. All right. So this is what our instantaneous power looks like for a generic circuit element or network. And then the average power is simply the DC part of the instantaneous power. So now let's go quickly here and talk about what the instantaneous power is going to look like for just a pure resistor, a pure inductor, and a pure capacitor. Once again, review of topics covered in circuits 1. And then once we wrap that up, we'll move on to the new stuff. Okay. So for a resistor, we know the following things, and these are the stuff that we figured out during our phasor relationships lecture. We know that the magnitude of the voltage drop across a resistor is equal to the resistance value times the magnitude of the current. And we also know that the phase angle of the voltage is equal to the phase angle of the current, right? We came up with those relationships about a week ago at this point, I believe. Or it would have been last Friday. So using these pieces of information, the instantaneous power absorbed by a resistor is going to look like 1/2 times the magnitude of the volt. Let's put everything in terms of the voltage first. So we're going to have Vm, and now I'm going to express Im in terms of Vm. So Im is equal to Vm divided by R. So we have Vm times Vm over R. So that's going to look like Vm squared divided by R. Now I have the cosine of theta V minus theta V. Well, what's the cosine of 0? 1. Okay, so I can just leave this part alone. 1 plus, I have that same 1/2 Vm Im, which we know looks like 1/2 Vm squared over R. So now I'm going to have cosine twice omega t plus twice theta V. Okay. The average power absorbed by a resistor only in terms of the voltage drop across the resistor is just going to be the DC part of this equation, which is just 1/2 Vm squared divided by the resistor value. Putting things only in terms of the current, we'll have 1/2. So Vm is equal to R times Im. So we're going to have R times Im, or Im squared times R. Cosine of 0 is still 1, plus the cosine of twice omega t plus twice theta I. So in terms of current, our average power is just 1/2 Im squared times our resistor value. So now, whenever we're dealing with a resistor, we literally don't have to know both the voltage and the current. If we know one, we have enough information to solve for the instantaneous power as well as the average power. So it's just a little shortcut that we get to use because we know how these things are related to each other. For an inductor, we know that the magnitude of the voltage is equal to omega L times the magnitude of the current. And we also know that theta V is equal to theta I plus 90 degrees. Okay. So the instantaneous power absorbed by an inductor in terms of the voltage, we're going to have the voltage by itself. And obviously, we can just rearrange this relationship right here and say that our current Im is equal to Vm divided by omega L. So that's going to look like Vm squared over omega L. And then we have, let me do this right. So what I'm about to do, I'm going to do this in a different color because I'm going to wind up erasing it here in a second, is cosine of theta v minus theta I, because that's the next part of our instantaneous power relationship right here, right? So theta v is going to be expressed as theta v because we're doing everything in terms of the voltage. Theta I could be written as theta v minus 90 degrees, right? If we pulled this 90 degrees from this side and moved it over here, we would see that theta I is equal to theta v minus 90. Which is going to look like the cosine of positive 90 degrees. What's the cosine of positive 90? 0. So we will not have a DC term at all, okay? So instead, we're just going to have that AC term. So that's going to be the cosine of twice omega t. And now I'm going to add theta v and theta I. So that's going to look like twice theta v minus 90 degrees. From this, we can see that our average power is 0. There's no DC term in our instantaneous power relationship. In terms of current, we're going to be doing a similar thing here. So instead of Vm squared over omega L, now we're going to have Im squared times omega L. Cosine of negative 90 degrees, or excuse me, cosine of positive 90 degrees is still 0, so the DC term still goes away. We're going to have cosine twice omega t plus twice theta I plus 90 degrees. Right? So those are our inductor relationships where everything is expressed only in terms of the voltage drop across the inductor or only in terms of the current flowing through the inductor. In review from circuits 1, hopefully. Lastly, we have our capacitor. So in a capacitor, the current magnitude is equal to omega c times the voltage magnitude. And we know that theta I is equal to theta v plus 90 degrees. So following a very similar derivation, we're going to wind up having 1/2 Vm squared times omega c times the cosine of twice omega t plus twice theta v plus 90 degrees. Average power is 0. Was there a question? C for a capacitor. And in terms of our current, this is going to look like 1/2 Im squared divided by omega c times the cosine of twice omega t plus twice theta I minus 90 degrees. And once again, our average power will be 0. All right, so because you guys had to, use and apply these relationships way back in circuits one. I'm not going to waste our time with a numerical example or anything like that because you should be able to apply everything. One thing that I do want to point out here, right? Just to make this very explicitly obvious, Vm is just the magnitude of the phasor voltage that we are interested in, right? So we have a time domain relationship for instantaneous power because our instantaneous power is varying as a function of time. But all of the parts that go into this relationship can be tied back to those phasor relationships so that we never have to do circuit analysis in the time domain because of how much of a huge pain in the ass it is, right? So we're going to pull things from our frequency domain or our phasor domain circuit analysis and literally just plug it into this equation when we need to apply it. So Vm is just the magnitude of the phasor voltage. Theta V is just the angle of our phasor voltage. Im is nothing more than the magnitude of our phasor current of interest. And theta I is just the angle of our phasor current, right? Another quick thing here, just in case you have to numerically solve anything like this. This angle right here, twice omega t, is expressed in radians because omega, by definition, is measured in radians per second. Radians per second times time is going to give us an angle in radians. This angle right here is something that's measured. I wrote angles, I meant degrees, sorry. Is an angle that is measured in degrees. So if you're going to numerically evaluate a problem like this, you either need to convert 2 omega t into degrees, or you need to convert the twice theta I or blah, blah, blah into radians in order for your calculator to be able to handle that. Because if you mix up the units of your degrees, you're going to get garbage out, right? So you just need to be consistent. Doesn't matter if you use radians or degrees, but it's one or the other, definitely not both at the same time. Okay. All right. So before we move on to our next topic, any question about instantaneous power in a single phase circuit like we've got here? Caden, yes, sir.
So that means the capacitors and inductors absorb no power.
No average power. Yes, they do not absorb average power. So let's, just as a quick thing here, because this is going to come back up when we talk about complex power and all that kind of stuff anyway. So let's say that this is the power absorbed by an inductor, and the power absorbed by a capacitor is going to look very, very similar. Okay. And just for my inability to draw sinusoids very well, I'm going to just arbitrarily say that the phase angle of our instantaneous power is going to be 0, so that I can just draw this as a nice sine cosine function, right? So something like this. Okay. So anytime our instantaneous power is above our horizontal axis, this means that we are absorbing power. And anytime our instantaneous power waveform is below the horizontal axis, this means that we are absorbing negative power or we are supplying positive power, right? So effectively, in our energy storage elements in an AC system, we see that exactly half of the time they absorb power from the source, and exactly half of the time they supply power back to the source. If we look back at our original graph that I drew here, this was for a generic network, right? So this span of time right here is effectively telling us that there are certain instances in time where our excitation source is actually going to be absorbing power because our energy storage elements wind up supplying power back to our source. When we have just a pure inductor or pure capacitor, that happens exactly half of the time. Okay. So because we never hold on to any power, we absorb it and then we send it right back out. We absorb it and then we supply it right back out. We see that there's no average power that's absorbed. So the power that's stored by a capacitor or an inductor in an AC system is actually incapable of performing any real work because it doesn't hold on to it for long enough to do anything. All right. Any other questions? All right. So moving along to our new topic. The maximum average power transfer. So way back before exam 1 in circuits 1, you guys learned about maximum power transfer for a DC circuit, okay? So you had a situation that looked something like this. Let's say that we had a circuit simplified down to the Thevenin voltage in series with the Thevenin resistance. And then connected to this practical voltage source representation of our network. We had some load resistor RL, where this was the voltage drop across our load resistor RL. And this is the current flowing through our load resistor RL. And so PL as a function of RL looked like, let's say, VL times IL, which should wind up being V Thevenin squared times RL over R Thevenin plus RL quantity squared, if my mental math is correct, which I believe it is. So this is our power absorbed by our load resistor. And it obviously depends on what the value of the Thevenin voltage is, the value of the load resistance is, and the value of the Thevenin resistance, right? The maximum power that could ever be absorbed by our load resistor occurred when RL was equal to R Thevenin. And we wound up getting, sorry, this should be 1/4, not 1/2, my apologies. V Thevenin squared divided by R Thevenin. Any of this sound vaguely familiar? Okay. So what we're about to do is something pretty similar, except that we're no longer going to be dealing with an AC circuit. We're going to be no longer going to be dealing with a DC circuit. We're going to see what happens in an AC circuit. Okay. So in an AC circuit, let's say that we have some phasor Thevenin voltage in series with some Thevenin impedance. And now we want to know under what conditions maximum average power transfer occurs to some arbitrary load impedance ZL. So I'm going to define this is my phasor voltage VL. And this is my phasor current IL. Well, about 10 minutes ago or so, we learned that the average power absorbed by a generic element is 1/2 times the magnitude of the voltage drop across that element. So that would be the magnitude of phasor voltage VL. So that's just taking the place of VM in our original expression, times the magnitude of our phasor current. So that's just the magnitude of our phasor current IL, times the cosine of theta V minus theta I. So this expression right here is literally just the instantaneous power relationship that we came up, or excuse me, the average power relationship that we came up with about 20 minutes ago. I'm just expressing it in very slightly different terms to tie everything back to the phasor quantities in our circuit that we're looking at, okay? All right, so by inspection here, we can see that the voltage drop across our arbitrary load impedance ZL is just our Thevenin voltage times impedance ZL divided by Z Thevenin plus ZL. So I got that using voltage division. Anybody have any problem with that? Pretty straightforward, right? Now what I'm going to do is I'm going to split my load impedance up into its real and imaginary parts, and my Thevenin impedance up into its real and imaginary parts, right? So I'm going to have my phasor Thevenin voltage times RL plus JXL. And now in my denominator, I'm going to add the real parts of my impedances together and add the imaginary parts of my impedances together, so that I have RL plus R Thev plus J XL plus X Thev. Anybody have a problem with this? Okay, so recall, let me do this in a different color, that for a generic impedance Z, it can be expressed in rectangular form as R plus JX, where R is the resistance, the real part of the impedance, and X is the reactance, the imaginary part of the impedance. All I've done is I've split all of our impedances up into their rectangular forms, and then I've added the real parts together, and I've added the imaginary parts together. Okay. All right, so the magnitude of this voltage VL will be the magnitude of my Thevenin voltage times RL squared plus XL squared to the 1/2. So that's just the square root of that. So that's literally just the magnitude of the numerator divided by the magnitude of the denominator. So all I've done there is say that the magnitude of that complex number is just the magnitude of each of the parts effectively multiplied by each other, which should hopefully make sense based on our knowledge of complex numbers. So I have an expression for VL. So I figured out what this part of my equation is. Now I'm going to do the same thing for IL. So using good old Ohm's law, we should be able to see that our phasor current IL is just our phasor Thevenin voltage divided by Z-Thev plus ZL. And once again, I'm going to break out those impedances to put them in terms of their real and their imaginary parts. Yes. So the magnitude will never contain a J because it is just the length of that complex number. It is not a complex number itself. So there will not be a J in there. So this is going to look like V-Thev phasor divided by that same denominator from before. RL plus R-Thev plus JXL plus X-Thev. And now that I have what IL phasor is, I can find the magnitude of it. So the magnitude of our phasor current is going to be the magnitude of our Thevenin voltage divided by the magnitude of that denominator, which will once again be RL plus R-Thev squared plus XL plus X-Thev quantity squared. And then we take the square root of that sum. So now I figured out what this IL bit here is, okay? So the last thing that we have to figure out is cosine theta VL minus theta IL. And this is a little bit more difficult. So what we're going to do is I'm going to look at an impedance in the complex plane. Okay. So this is my real axis corresponding to R, and this is my imaginary axis that's corresponding to the X or the reactance, right? So for some generic impedance, Z is equal to R plus JX the magnitude or the length of this guy is just the magnitude of our impedance Z, where the magnitude of Z is just the square root of R squared plus X squared. Exactly the same relationship that we were using up above, right? Well, this angle right here, theta Z, is by definition theta V minus theta I, right? Because we know that impedance Z is equal to the ratio of our phasor voltage to our phasor current. So that's Vm over Im with an angle of theta V minus theta I. Okay. So from this graph, let me spell this out even further, the projection of our impedance vector onto the real axis is R. The projection of our impedance vector onto the imaginary axis is X. So what should the cosine of that angle be? So when I was in you say X over Z? R, right? So cosine should be the adjacent over the hypotenuse, right? This theta Z right here. So this is the adjacent part. This is the hypotenuse part. And then the opposite would be over here, right? So sine would be X over the magnitude of Z. Cosine of theta Z is going to be R over the magnitude of Z, right? So we can say that the cosine of theta VL minus theta IL is XL divided, oh, damn it, now I've got it backwards, RL over RL squared plus XL squared square root. Are we okay with that? So now I know this part. So I'm literally just going to multiply those three different parts we figured out together and see what shakes out. And so what we should see is that our average power is 1/2 times, so VL, or the magnitude of VL, let me scroll up here, so that's V thev magnitude times RL, squared plus XL squared to the 1/2 power divided by RL plus R thev squared plus XL plus X thev squared to the 1/2 power. Make sure I translated that over correctly. Seems like I did. Now we put in the magnitude of IL. Yes. It absolutely is. Thank you for that. Over here, we're going to have the magnitude of V thev divided by that exact same denominator. And then lastly, we're going to have that cosine bit, which is just RL divided by RL squared plus XL squared to the 1/2 power. So hopefully we can all see that this guy right here cancels that guy there. And this big ugly denominator thing is the square root of something multiplied by the exact same thing. So we're going to get rid of that square root sign in the denominator. And so our average power in general looks like 1/2 of the magnitude of our Thevenin voltage squared times RL divided by RL squared plus R thev squared plus XL. Damn it, there shouldn't have been a square here. My apologies. X thev squared. Like so. All right. So we're in the home stretch now. We've done a pretty considerable amount of complex math substitutions and all that kind of stuff to get to this point. So let me ask you guys a question. What is the reactance doing here? I know it's an odd question and I'm not, yeah. Any thoughts? Yeah, what is it doing to the average power? Making it smaller, exactly right. So because the reactance only shows up in the denominator, if we have any reactance whatsoever, it is making the average power smaller. So in order for maximum average power transfer to occur, that means XL has to be equal to negative X thevenin, which will make the reactive powers effectively cancel each other out, or the reactive portions cancel each other out, okay? So for maximum average power transfer to occur, XL has to equal negative X thev, right? So if our reactances cancel each other out, then by definition, P average will be larger than it was if the reactances were in there. Okay. Now let's look at what our relationship looks like when those reactances cancel each other out. So let's call this P average prime. So we're under the constraint that our reactances have taken care of each other. We now have 1/2 times V thev magnitude squared times RL divided by RL plus R thev squared. What do we do to maximize that? Yeah, so the short answer is we look way back up here to where we had a DC circuit and realize it's the exact same relationship as we had earlier. So we don't really need to do anything because we've already done the work. We know that maximum power transfer occurs when RL is equal to R thev based on this relationship. And that's literally the exact same relationship that we now have when our reactances cancel each other out. So in order to maximize P average prime, we need RL to be equal to R thevenin. Putting these two things together, we can say that maximum average power transfer occurs when our load impedance ZL is equal to R thev minus J X thev, or simply the conjugate of our Thevenin impedance. So these are the conditions under which maximum average power transfer occurs in an AC circuit. If our load is equal to the conjugate of the Thevenin impedance, we will have maximum average power transfer. And if we substitute in our relationship, we're going to wind up having P average max comes out to be the magnitude of our Thevenin voltage squared divided by our Thevenin resistance, and then we're going to have a factor of 1/8, because in a DC circuit, we had a factor of 1/4, and in that AC circuit, we have that pesky 1/2 factor out in front. So that says P average max. Wait, which part are you talking about? Maximum average power transfer occurs when ZL is equal to Z Thevenin conjugate. While we didn't derive this for a Norton equivalent circuit relationship, we can figure that out very easily, effectively, just by doing a source transformation. And so that's going to look like 1/8 the magnitude of our Norton current squared times our Thevenin resistance. All right, that didn't take as long as I thought it would. So now I got to figure out what to do with the next 25 minutes. So yes.
Not related to what we're doing, but are you going to upload PDF notes from your speed run from?
Video's up. Watch the video.
Oh, really?
Yep. Or I will come to my office and I will give you the notes and you can scan them so that I can be lazy, and then I'll upload that because I'm just too lazy to scan them myself.
Okay, I'll do it.
Yep. Sounds great. All right. So before we move on to something else, which will probably just be getting a little bit ahead so that we can spend more time talking about complex power in a couple of days. Is there any questions on this, Isaiah? You forgot what a conjugate was. Okie dokie. So let's review that real quick. Oh God. Okay. So let's say that I have a complex number. So here's my complex plane. This is my real axis. This is my imaginary axis. And I'm going to call this complex number A, so that the projection of A onto the real axis has a real part, lowercase a, and the projection onto the imaginary axis is lowercase b. So in rectangular form, I don't need that magnitude sign there, excuse me. My complex number A is equal to A plus JB. While we're at it, let's express it in polar form, right? So in polar form, I'm going to have my magnitude. So that's the length of vector A. And this is my phase angle, A. So in polar form, we have magnitude of A, angle, phase angle of A. We good with how we have defined A? Okay. The complex conjugate of A is literally just taking complex number A and flipping it over the horizontal axis. So A conjugate would be this guy down here. So notice that the projection of that onto the real axis is still just A, but the projection onto the imaginary axis is negative B. So, damn it, I keep putting these absolute value signs when I don't need them. So A conjugate is just A minus JB. And in polar form, our vector didn't change length at all. So it still has a length of the magnitude of A. but now it has an angle of negative theta A. So that's the magnitude of A, angle negative theta A. So when we're performing the complex conjugate operation, all we're doing is we're changing the sign on the imaginary part if we're dealing with a rectangular form complex number, or we're changing the sign on the angle if we're dealing with a polar form complex number. And just as a heads up, that's something that we're going to be doing a lot. So reviewing it now wasn't necessarily a bad thing because we're going to do a crap ton of it in a couple of days when we're looking at complex power. So anyway. All right. Any other questions about what we covered today before I just go off on a completely different subject? All right, so let's talk about effective values of periodic waveforms. And it's, I think this will kill the next 20 minutes or so. All right, so I guess I'll do my regular circuits one spiel for this because not all of you had me for circuits one. So for those of you that did, sorry, you're hearing the same bullshit again. It happens. Okay, so there are outlets in this room. I'm going to draw a shitty picture of an outlet. This is a shitty picture of an outlet. Okay. There are three different terminals on this outlet. So here in green, I'm going to put our ground pin. Not all outlets have a ground pin because not all outlets were installed before the code got updated. So that's a good way to tell whether or not your house or whatever is up to code. If it doesn't have a ground pin, technically speaking, you really need to change that outlet. Okay. Also, you really need to install a ground wire in your home also, or bad things can happen. All right, then over here on the left-hand side, we have our neutral wire. Our neutral wire is effectively the negative polarity terminal of our receptacle. Okay, but it's not really a negative polarity terminal because we know that our voltage is constantly changing between positive and negative because it's an AC voltage, right? So I'm going to put a thing up here. And then our hot wire, which I'll do in black, will be up here. So that the voltage that our outlet is supplying is measured between the hot wire conductor and the neutral wire conductor. So what is this voltage? 120, okay? So I both agree and disagree simultaneously. I know, it's amazing, right?
Yeah.
So Michael said that this was 120 volts. Get that in a second, but you're right. Okay. So 120 volts is by definition a DC voltage, and we have an AC system. Okay. So if we were to take an oscilloscope and we were actually to plug our voltage probes into an outlet, what we would find is that the voltage as a function of time measured between the hot wire and the neutral wire in an ideal situation would be 120 times the square root of 2, which I think comes out to be 169.7 or so, cosine 120 pi t plus some phase angle that really just depends on when we start our measurement occurring. Okay. The 120 volts that we commonly hear is what's called the RMS voltage. And it is the effective value of this sinusoidal periodic waveform. So instead of carrying around all of this information, we choose to only carry around a part of it. Okay, so let's talk about what that part of it actually represents. The effective value of a periodic waveform is the equivalent DC signal, so voltage or current, that delivers the same average power as the periodic signal. So let's say that we're dealing with a resistance, because we know that the average power delivered to a resistor is not zero. So we're dealing with something to actually look at, right? So for an arbitrary resistor R, the average power, and this is going to use a mathematical relationship that I didn't discuss today, but I did discuss back in circuits 1. So once again, if you want to know where it comes from, go to my shitty YouTube channel. Okay. So we are going to have 1 over the period of the integral over 1 period of the voltage squared divided by the resistor value, and we're integrating with respect to time. So that's in terms of a periodic voltage waveform. So I'm just going to put out here, V of t is a periodic voltage. Just in case we had a periodic current waveform, we could write this as P average is equal to 1 over t times the integral from 0 to t of I squared of t times R dt, where I of t is a periodic current. And then in terms of DC voltages and currents, we know that our average power is just the power absorbed by our resistor in a DC system, right? Only going to have one value. So that would look like either our DC voltage squared divided by the resistor value, or in terms of current, our DC current squared times our resistor value. So what we're going to do to figure out how to calculate an effective value is we're just going to equate our average power relationships to each other and then solve for the DC voltage or the DC current. Okay, because once again, our effective value is the equivalent DC value that delivers the same amount of average power. So for voltages, we could say that VDC squared divided by R is equal to 1 over T, the period of our periodic voltage signal, times the integral from 0 to T of our periodic voltage waveform squared divided by our resistor value. And it looks like I have a common factor of 1 over R on both sides, so I can get rid of those. Turns out the value of the resistor we're finding the average power over doesn't even matter. Okay. So now I'm just trying to get VDC by itself on the left-hand side of the equation. So all I need to do is take the square root of both sides. So our effective value for our voltage is just the square root of 1 over t times the integral from 0 to t of the square of our periodic voltage waveform with respect to time. We can do an incredibly similar derivation using our current relationships, and what we will find is that our effective current is the square root of 1 over t times the integral from 0 to t of our periodic current waveform squared with respect to time. So it's literally the exact same equation, except when we're finding the effective value for the current, we square the periodic current. When we're finding the effective value for the voltage, we square the periodic voltage. All right. Typically speaking, RMS voltages are measured in units called VRMS, and RMS currents are measured in currents with units of amps RMS. So this RMS designation comes from the fact that we are taking the square root of the arithmetic mean, that's just a fancy word for average, of the square of our signal. So RMS literally tells you what mathematical operations we're performing on our periodic function to get the effective value. Okay. All right, so got another 10 minutes to kill. Let's look at a rectangular pulse. So this is a pretty commonly used voltage waveform in electrical engineering, current waveform as well. But let's just say that it's for the sake of argument. So let's say that I have some time-varying voltage V of t. Here's time. And let's say that our voltage has some magnitude, let's call it V naught. And so it's at V naught for some amount of time, and then it's at 0 for some amount of time, and then it goes back up to V naught for the same amount of time, and then down to 0 for the same amount of time, and so on and so forth like this. Let's call this point in time right here capital T, because that's the amount of time it took for one period to elapse. This point in time right here will be 2t, et cetera, so that we see that we have a periodic function. And this point in time right here will be x times capital T, where x is, let me write it as this way. 0 is less than x is less than 1, and x represents the duty cycle of the waveform, right? So all a duty cycle means is what percentage of the time it's on compared to off. So if we have a rectangular pulse signal like this with a duty cycle of 70%, or X is equal to 0.7, it means that 70% of the time the voltage is at V naught, and the other 30% of the time the voltage is at 0. That's all duty cycle means, okay? So we are going to figure out what the effective value for any arbitrary periodic pulsed voltage waveform like this would be as a function of its duty cycle, okay, which is an interesting thing to know. So over one cycle, our voltage waveform could be written as V naught for 0 is less than T is less than X capital T. And then our voltage is 0 volts for X capital T is less than T is less than capital T. Anybody have any problem with how I've chosen to represent this signal as a piecewise function? Anybody unclear about what's going on? All right. So if I want to find the effective value, I'm going to use my equation. The effective value is the square root of 1 over the period times the integral over 1 period of our voltage waveform squared with respect to time. That's our generic equation. And now I'm going to plug stuff in here. So the period of our function is capital T. Because I have a piecewise function, I'm going to have to split this up into two integrals. So I'm going to integrate over each interval like so. So my first integral will be from 0 to xt. And I'm going to be integrating my voltage, which is V naught, but I'm integrating the square of my voltage. So I'll have V naught squared like so. Dt. And then for my next interval, I will be integrating from xt out to t, and my voltage is 0. So before we do the math here, does anybody have any questions, comments, or concerns about how I've set up my integrals? All right. So integral of 0 is 0. So we don't have to worry about that part literally at all. So now we're just going to play around with this other part. Well, that's going to look like the square root of 1 over t. So our voltage is a constant, so I can actually pull that outside. So we're going to have V naught squared. And now I'm integrating dt from 0 to xt. I'm just going to keep doing this on the same line. So what's the integral of dt? T, right? So that's just going to look like the square root of 1 over t times V naught squared times xt minus 0. And I can see that this t here in the numerator cancels this t here in the denominator. And what I'm left with is V naught times the square root of x, my duty cycle. So that's my effective value of a periodic rectangular pulse with a duty cycle of x. So if my duty cycle is 50%, then that would be V naught times the square root of 1/2, or V naught over root 2. All right, we got 3 minutes left. Well, that took longer than I wanted to. All right, we'll do a sinusoidal function at the beginning of class on whatever day we meet next, and then we'll go on from there.